Alright, today we're taking a look at factoring out common factors from an expression. Before we can do that though, we need to take a look back at the distributive property which we just took a look at last time. So if you can, from memory, take a pause and just write down what the distributive property is. Alright, I'm assuming you've done that at this point, and hopefully what you wrote down was this, that A times the quantity B plus C is equal to AB plus AC. Meaning that if we have multiplication outside of parentheses, as long as we distribute that multiplication to both terms, we're kind of allowed to break order of operations there. It's just another way of writing that expression. So let me ask you this. We've been going kind of one direction on this. We've been taking this left-hand side and turning it into the right-hand side because that's what's fit our purposes. We're able to write a simpler expression that way, able to simplify better that way. But what if we wanted to go the other way? What if we wanted to take this right-hand side and turn it back into the left-hand side? Would we be able to do that? Is that allowed for us to do? Hopefully you're thinking to yourself, yes, that's what an equal sign is. Remember, an equal sign means we are the same. So turning the left side into the right side is okay because they're the same, which also means turning the right into the left is got to be good too. So how does this apply to taking out the greatest common factor? Well, let's take a look. Suppose we had an expression like this. Let's take something really, really easy. 3x plus 4x. Okay, now I don't want you to combine like terms here. You could combine like terms. We're going to talk about that tomorrow and add these two things together, but I don't want you to do that. I just want you to think what part of each of these terms might have been distributed in the previous step. Well, I'm looking at it, and I see they both have an x, just like in our distributive property, both terms have an a. So if I were to write this in reverse, I would say that this might be the same thing as x times 3 plus 4. Now, you could put the x before your parentheses, after your parentheses. It doesn't particularly matter. This is what we call factoring out a common factor. Okay? We can do this too with just plain numbers if that's easier. So think for a second about what the greatest common factor of 8 and 12 would be. Hopefully you can remember how to figure out greatest common factor. Greatest common factor of those would be 4. Well, how would this work with distributive property in reverse, or factoring out the greatest common factor? Well, we could rewrite each of these as 4 times some other number. Okay, with 4 being the greatest common factor. Then we could take our distributive property in reverse and rewrite this as 4 times 2 plus 3. Okay, this is what factoring out the greatest common factor looks like. Now with variables, when we have a lot of them, more than just a simple single x up here, it can get a little bit more complicated. Okay, so suppose we had something like 3x squared plus 2x. Here we have x's in both, but one's an x squared and one's an x. Is that okay? Well, we can actually write it in a way that shows that both of these are just different forms of multiplying something by x. So the first one, 3x squared, we could rewrite as 3x times x, because x times x is x squared. And the other one is just 2 times x. It's already kind of written that way. We now say, okay, the x must have been distributed in the previous step. Working our way back, we're left with a 3x plus 2. This example of factoring out a greatest common factor is kind of closer to what you'll see as something useful. You see, up here, with these first two examples that we looked at, we were able to factor out the greatest common factor successfully, but it didn't necessarily help us get anywhere. Like, 8 plus 12 is 20. usually we're just going to want to make that into a 20, so writing it in this way isn't necessarily all that helpful. This, on the other hand, we're going to see lots of uses for factoring out the greatest common factor when we have lots of variables involved. So the first thing you need to be able to do is identify the greatest common factor. Okay, so I've got a whole section here where we're going to practice finding the greatest common factor. Now if it's numbers, hopefully you remember how to do that. All you're trying to do is figure out the largest number that both of your terms divide nice and evenly by. So GCF of 12 and 8, pause if you want to try these on your own, but I'm going to kind of go through them pretty rapidly, but definitely pause if you want to try them on your own. So GCF of 12 and 8 is 4. That's our GCF. Now looking at, if we throw an x in there, well, now it just becomes 4x. That's easy enough because we could rewrite, again, the way that I know is I could rewrite both of these as 4x times something. This first one's 4x times 3. The second one is 4x times 2. That's how I know that's my GCF. There's no bigger number that I could use, and there's no more in the variable area that I can use. C is kind of a fun one. Again, pause if you want. GCF here is still 4x. Okay, there's two x's because we have an x squared in the first one, but there's only one x in the second one, so they only have one x in common. Definitely pause D and try this one on your own. This is a little bit of a tricky one, but I really think it's pretty cool. Alright, I'm assuming you've tried that out. So the way you want to do this is you kind of want to look at it in parts. What's the GCF of my numbers? What's the GCF of my x's? What's the GCF of my y's? Okay, because I've got all three of those things in there. So the GCF of 3, 6, and 12 is 3. This one has two x's, but the other ones each only have 1. So like if I were to rewrite it, I'd only be able to use a single x. I'm not going to be able to write them all with an x squared times something because the second two don't have two x's. So that's not going to work. The y's, I have 3 in this one, I have 4 in this one, but I've only got 1 in this one. So 3xy is my GCF. Again, I could pick any one of them randomly. I could rewrite 6xy to the fourth as 3xy times 2y cubed. And that would work great. Okay, so now we're going to practice actually factoring out the GCF from several expressions. What you want to do is you first want to identify the GCF. Okay, so I'm going to even write that down by these first couple here. And then you want to rewrite each term in the expression as the GCF times something else. Okay, so my GCF up here in this first one is 3. Luckily, this one's already kind of written nicely for me as 3 times x plus 3 times y. Then you just take your distributive property in reverse. I get 3 times the quantity x plus y. Why don't you go ahead and try B, pause, and then come back when you're ready to go. Alright, GCF is 8. So I can rewrite 16D as 8 times 2D minus 8 I can rewrite as 8 times 1. You do need that 1 in there. That is extremely, extremely important that you have that in there. Okay? Because now when you do distributive property in reverse, you get 8 times 2D minus 1. That 1's important. If you don't have that 1 there, this is just 16D. You don't end up with the minus 8 if you don't put the minus 1 there. Why don't you just try the next 3 on your own? I think you can do it. So give it a try, and then we'll go through them one by one. Alright, I'm assuming you've done that. And let's label some GCFs. I'm going to label my GCFs in all 3 first. So the GCF of x squared minus 9x is just x. There's no number that I can divide 1 and 9 both by, other than 1, but we don't typically use 1 as a GCF. 12x squared minus 4x, I can divide 12 and 4 by 4, and they each have at least one x. 4ax plus 12bx, this one's still just 4x too, guys. There's an a in one and a b in the other, but it's got to be in both terms to be able to rewrite each term as being something multiplied times that. Okay, again, rewrite as GCF times something. So this one, x times x is x squared, minus x times 9 is 9x. Then do distributive property in reverse. This one I can do 4x times 3x is 12x squared. And again, very key that I put that 1 there, 4x times 1. Factor out the GCF, distributive property in reverse, and we're looking good. Same thing for the last one, it's 4x times a, and 4x times 3b, 4 times 3 being 12, distributive property in reverse. Question that I get a lot is, do I have to write down that step? Do I have to write down that intermediate step? The answer is no, you don't. However, I think it helps when you're first starting off this, when you're doing practice problems on this, I would strongly recommend that you do that. The reason that I suggest that you do that is simply because if you don't get your GCF right, that's going to be the harder part to figure out. But if you don't get that right, you aren't going to be able to write both terms as the GCF times something. Something's probably going to go wrong there. There are some other errors you can make where you might still be able to do it. Maybe you didn't pick the greatest common factor. Like for this last one, if you pick 2x, that could be a problem too. But again, it's part of the reason why I kind of want you to show what's going on there. That's it for today. Sorry for another long video. Hopefully the next one will be a little bit shorter. Try some practice problems, take a concept quiz. Good luck.